graphs. I am recording. Actually, that said, last class I forgot to record. So could you guys please remind me? Just like, it's for you. You see I'm not recording. You guys see the little recording button in the top corner, right?
Yes.
If you don't see that, be like, Audrey, record, please. And then we're good. Also, reminder, it's really wonderful and helpful if you turn on your cameras, and some of you suggested that you would be willing to do that. So strongly encouraged to turn on your cameras. Yay, hi. Okay, all right, so today we're gonna move into actual functions, and we're gonna be doing something called limits by direct substitution. So my first question for you guys is, what does it mean to be continuous? So this is what we did last class. What does continuous mean?
When like the function is like you don't have to lift up your pencil while drawing it.
You don't have to lift up your pencil when drawing it, exactly. And when we talked about like limits in terms of expectations, reality, that type of stuff, what does it mean? Can we talk about it in terms of expectations and reality?
Is it when like the expectation meets the reality?
It's when the expectation meets the reality. You got it. So continuity is when you're looking at a graph and you don't have to pick up your pen, or when the expectation and the reality are both there. We have an expectation and we have a reality, and they are the same. So limits by direct substitution, we have this theorem from that. And this theorem is basically the definition of continuity. It tells me that if f of x is continuous at x equals 2a, we just said that what continuous means is for the expectation to meet the reality, then the limit as x approaches to a of the function is equal to f of a. So that seems kind of like duh, because that's the definition of continuity as well. But it actually is giving us some really important information about how we can evaluate limits. So in other words, what this is saying is, if f of x is continuous at x equals a, then to evaluate the limit, we can just plug in a. Now, another way to think of this, where we stop using new words, is, well, as of right now, when we look at a graph, we can tell if something's continuous, but we don't really know how to look at a function and know where it's continuous. So another way of saying this is, if x equals a is in the domain of f of x, and f of x is not a piecewise function, then to evaluate the limit, plug in.
Sorry, what's a piecewise function?
So those are we have two questions we have to answer about these words. That's the second one, but we'll start with it since you asked. What is a piecewise function? Does anyone remember?
It's like, I'm really trying to remember, but it's when there's multiple functions, right? Like
Exactly. So a piecewise function, and we're just going to kind of briefly explain it right now because later today we're going to do a huge piecewise function review when we calculate limits from piecewise functions. But a piecewise function is a function that's defined by multiple functions. So instead of just f of x equals x, we'll have f of x equals x sometimes, but some other times maybe it equals 5. So right now, just kind of think of this as a piecewise function defined by multiple functions. So if it looks normal, then it's not piecewise. So I'm just going to do, so that would be an example of a piecewise function. We have it defined by multiple different functions. Again, we'll do a big review later. This is just to kind of start you off. Second, the domain. What are some things that could happen for x to not be in the domain of my function?
some asymptotes.
Asymptotes, okay. But what could happen? So yes, asymptotes for sure. A lot of times that's going to happen. But what could happen when we're looking at the function? When we plug in x, what might happen that tells us that, oh, hey, look, that value wasn't in the domain?
When it's an empty hole or like empty dot?
Okay, yes. But again, I want us to not think about it in terms of graphs, but in terms of plugging into a function. So like, for example, you have a calculator. You plug into a calculator and your calculator gives you an error. What might you do that would cause that? Luca?
Divide by 0?
Oh, David? Luca?
Divide by 0?
Division by 0. What's another thing that could happen? What's the square root of 4?
2.
2. Did that make sense?
Yeah.
Is there a value I could plug into a square root that wouldn't make sense?
Negative.
Negative. So when we're talking about the domain for the purposes of this class, mainly we're talking about division by 0 and negatives under square roots. So no division by 0, no negatives under a square root. The best way to understand what this is saying, though, is to just get started. So evaluate the following limits. Or state that we do not yet know how. I need water. I'll be right back. So the limit as x approaches 5 of 2x plus 1. What happens when I plug in 5?
We got 11.
Get 11.
I get 11. Is 11 a value that makes sense?
Yeah.
Yes.
Is 5 in the domain of 2x plus 1?
Yeah.
Didn't cause division by 0. Didn't cause a negative under a square root. It's in the domain. This is my
Wow.
answer. The answer is 11. I'm done.
Wow.
Yeah. Okay, what about if though I were to do the limit as x approaches 2 of 5 over 2 minus x? What happens when I plug in?
It goes to divided by 0.
I get that division by 0.
Wow.
So here, plugging in gives 5 over 0. Was division by 0 one of the problems? If you plug 5 over 0 into your calculator, will it give you an error?
Yes.
Yes. So is 2 in the domain of this function?
No.
No. So the theorem does not apply. We don't know how to do this yet. What happens when I plug in?
You get 3.
I get 3. Is 3 a number that exists and that makes sense?
Yes.
So that's my answer. The theorem applied, 3 is in the domain, we are good. So what if I were to do then the limit as x approaches 1 of a half minus x?
Give square root of minus 0.5, which is impossible.
Square root of minus a half? Impossible. It's not in the domain. Does the theorem apply?
No.
Nope. We don't know how to do this yet. Okay, what if I were to give you this? What happens when you plug in?
It
0
goes to
divided
0
by
over
7?
7.
You're getting 0 over 7, and when you plug 0 over 7 into your calculator, what do you get?
0.
You get 0. You don't get an error. So the 0 on top, does that make sense? Is that okay?
Yeah.
Yep, that's my answer.
Sweet.
Hmm?
Yeah. 24 over 18, I think. 25.
28.
Oh, right. It's a plus. Yeah, I thought it was a minus. My bad.
And 6 over 7 is my final answer. That made sense. Let's just do one more. Let's use this exact same function that we have right here. And we'll have the limit as x approaches 1 of this function instead of 5. What happens when I plug in?
0 over 0.
I get 0 over 0.
Mm-hmm.
Is that division by 0?
Yeah.
Yes.
Yes. So is x equals 1 in the domain of this function?
No.
So can I use the theorem?
No.
No.
No. I don't know how to do this yet.
What if it's infinity?
What do you mean, what if it's infinity? Like, what if
Like-
plugging in gives infinity?
Yeah.
So the only way that plugging in could give infinity is if you have the limit approaching infinity itself, which we're going to deal with later, or it turns out that b is going to give infinity as well, and we're going to talk about that a lot later. So like, in other words, the only way for it to give infinity is if the value is not in the domain, because remember, infinity doesn't exist. So we'll deal with that later. Or if we have the limit as x approaches infinity, which we're not really looking at right now. Does that answer your question?
Good, thank you.
Did that actually answer your question?
Yeah.
Okay. Okay, so x equals 1 is not in the domain. We don't know how to do this yet. So basically what we just saw here is if when you plug in, it makes sense, then that was probably the right thing to do, and that's your answer. If, however, when you plug in and your calculator gives you an error, then you got to do something else. And we just don't know what those somethings else are yet. And this method is called direct substitution. So are there any questions about any of the problems that we just did? Good. So if plugging in makes sense, then plugging in gives us the answer, then we can actually extend this to what if we know what the limits are, but we don't actually know what the functions are? So what we're going to be doing here is applying something called limit laws. Except I'm not going to teach you guys what the limit laws are because I find that they tend to just confuse people and get in the way. We're going to really just think about it in terms of the theorem that we just stated. So to understand what I'm talking about, let's say that I have 3 different limits. So here I have 3 functions. I have f, g, and h, and I know the values of their limits at 2 without actually knowing what the functions are. So what if I were to then ask you for the limit as x approaches 2 of g of x times h of x? What we just said is if plugging in makes sense, then just plug in. I know the limit as x goes to 2 of g of x, and I know the limit as x goes to 2 of h of x. So what do you think this is going to give me?
Multiply 5 by 6.
Just multiply 5 by 6. I already know those limits, so I can just kind of plug in, and I get that my final answer here is 30. Or what if I were to ask you for the limit as x approaches 2 of the square root of h of x minus 2? What's that going to give me?
Two.
2.
2, because again, if plugging in makes sense, just plug in. So I plug in, I get the square root of 4, I get a 2. And that's my final answer. What about, though, if I were to ask you for this? What would this give me?
Error.
Error, because plugging in is going to give me a 0 over 0. So plugging in does not work in this case. It gives me an error. So here we would just say that we don't have enough info. Let's do one more. So what happens here? Can I still just plug in?
Yeah, I think so.
Yep. So I'll
Is
get
29?
3.
Is it 29? 10,
15 plus 10, that's 25.
oh, it's
Almost
20,
7?
27, because here we're going to get the square root of 4,
Yeah.
which is 2, and then plus 10, or rather plus 5 times 2, and that gives us a 27. So this kind of goes back to that same theorem. If plugging in makes sense, great, just plug in. If not, well, then we can't do it in this case. Are there any questions about these problems that we did here? Okay, so I'm just going to briefly go back up to the theorem. The theorem, our final part of the theorem said, if x equals a is in the domain of f of x and f of x is not a piecewise function, then to evaluate the limit, plug in. So that's what we've been doing with all of these problems. So now the next question is, well, what exactly is a piecewise function? We kind of had a brief reminder there, but we'll do a bigger reminder now. And what do we do in the cases of piecewise functions? And so we're just going to start this with an example, and that way we can really kind of get into the piecewise function. So this is my piecewise function. We're saying that f of x is equal to 2x plus 1 for all x values that are less than 3, and f of x is equal to x minus 4 for all x values that are bigger than or equal to 3. So I'm going to start off by graphing this thing. I'm not going to ask you guys to graph piecewise functions. I'm just going to do it right now to make sure that we kind of understand and connect this back to what we've been doing. And also maybe help us understand what this is saying. So this is saying that we have this graph, and on the right side of 3, so over here on the right side of 3, if I have this line at 3, I'm going to erase this line at the end, but on the right side of 3, the function should be defined by x minus 4, and on the left side of 3, the function should be defined by 2x plus 1. How do I graph 2x plus 1? What shape is that going to take? You got it.
Straight line.
Just going to be a straight line. There you go. So we're going to graph that. At 3, that straight line, so I'm going to erase our separation line right now. At 3, that straight line takes the value of 7. So I'm going to go 1, 2, 3, 4, 5, 6, 7. And on the left side of 3, we're going to have this line that has a slope of 2. So that line right there is 2x plus 1. And on the right side of 3, what's x minus 4 going to look like? Yeah, you got it. It's going to be a straight line that has a slope of 1. So when x equals 3, the value it takes is -1. And it's just going to have a little bit of a more lenient slope, gradual slope. So the way that I've drawn this, I have it kind of going through the whole thing. Which side of that hole should it be on? We're saying
Right.
bigger than 3. So this stuff over here on the left side is not important. I only care about the part that's on the right side. Now, which one of those open dots should I close?
The bottom one.
The bottom one, because
Bottom one.
x minus 4 is the one that goes with x greater than or equal to 3. So that's going to be a closed dot right there. Now this x equals 3, this place where we changed from one function to the other, we are going to refer to that as the breakpoint of the piecewise function. So here x equals 3 is the breakpoint. So the breakpoint of piecewise functions are all of the values that show up in the inequalities. So looking at this graph now, is there a place where this function is not continuous?
No. Oh yes, one. Sorry.
Okay, at what x value is that?
3.
3, at the breakpoint. What kind of discontinuity does it have there?
Jump.
A jump, right? Because we have our graph coming in at one place and then going out at the other place. They don't kind of like connect there, they're separated. So that's a jump discontinuity. So this is what our graph looks like. We're going to try to use this graph to help us understand how we would evaluate this without the graph. So I'm going to ask us about a few different limits here. Let's start with the limit as x approaches 2 of f of x. I'm going to start off by doing this on the graph. If I go to a graph, do I look at 2 exactly, or do I go to the left and right of 2? Do I just go and be like, here's 2, there's the value, or do I say, let's look at the left and let's look at the right and let's see what happens as we're on our way there?
Look at the left and right.
I'm looking at the left side of 2 and the right side of 2. Good. Which function am I on when I do that? 2x plus 1 or x minus 4?
2x plus 1.
I'm on 2x plus 1. I'm on that top line. So what that means is down here, I can say this is the limit as x approaches 2 of 2x plus 1. Now, if we didn't have the graph,
Just look at the x.
we just look at the x values, the intervals there. We're looking at 2. We want values left of 2 and right of 2. So like 1.9 and 2.1. Which interval are those two numbers on? The top one or the bottom one? The top one. 2 from the left is less than 3. 2 from the right is also less than 3. So 2 from the left, that's like 1.9, that's like 2.1. So we take the top function. But now I can just use the theorem that we just had, which was that if we plug in and it makes sense, then that's our answer. So what does plugging in give us here?
5.
5, that's our answer. What about f of 2?
Doesn't exist.
This is telling me to look at the interval where 2 itself is. Where is 2? Not 2 from the left, not 2 from the right, but 2 itself. Is it on the top or the bottom?
The top, sorry.
The top. So 2. In this case, I'm looking at 2 itself. 2 is less than 3. So this is 2 times 2 plus 1. Do I also get 5?
Yeah.
Are these two things equal?
Yeah.
Is this continuous here?
Yeah.
Yeah. And if we look at the graph, can we also see that it's continuous there?
Mm-hmm.
So I'll just remind you guys, remember we said that continuity occurs when expectation equals to reality. In this case, we see our expectation equaling to our reality. So this is continuous. What if I were to ask you about, I'm going to go up here so I have space to do everything I want. The limit as x approaches 4 of f of x. Again, I'm looking at the left side of 4 and the right side of 4. So I want to know what interval is 4 from the left on, what interval is 4 from the right on. So that's like 3.9 and 4.1. Well, where is it?
It's on the bottom function.
They're both on the bottom. Those are both bigger than 3. So I'm going to replace this with x minus 4. And I'm going to get a 0. And that's my final answer. Which means that 4 is actually way over here. Kind of drew that back graph a little badly. Okay, what about f of 4? This is saying, where is 4? Four is
0.
also bigger than 3. So this is just 4 minus 4, which gives me a 0. Are these values the same? Is this
Yeah.
continuous?
Yeah.
Yeah. Okay, so both of those were pretty straightforward. Now the question is, what happens if I ask for the limit at the breakpoint? So if I'm looking for the limit as x approaches 3 of f of x, I'm looking for 3 from the left and 3 from the right. So remember, 3 from the left, that would be like 2.9. Where is that? Which interval is that on?
On the top, the 2x plus 1.
The 2x plus 1, the top one. So that's less than 3. And 3 from the right, that would be like 3.1. Which interval is that on?
And x minus 4.
So that's bigger than 3. So notice that when I'm doing the breakpoint, 3 from the left and 3 from the right are on different intervals. So what that means is I'm going to have to take this and look at the left and right limits separately. So I'm going to look at the limit as x approaches 3 from the left of the function and the limit as x approaches 3 from the right of the function. Well, we just said that 3 from the left is less than 3 and 3 from the right is bigger than 3. It's going to be helpful to get used to labeling piecewise functions when you see them in that way. So I have x less than 3 and x bigger than 3. So on the left side, the function I end up with here is 2x plus 1. Whereas on the right side, the function I end up with is x minus 4. take a second, make sure you understand what's happening here. Are there any questions?
So at the first part,
Yeah.
So you just plug in, like let's say for the first one where it's x is 2.
Mm-hmm.
So you just take the top function and then you just plug in 2 and then you check to see if it is the same.
So I'm kind of thinking of this as if it was two different questions. That was one question, that was another question. So really, it's just the first part of your answer. You take the function, the appropriate function, and you plug in.
Okay.
The end.
Okay, so what if it wasn't the same?
What is it?
Like the second part.
If the second part were different, then that would mean it's just not continuous,
Okay.
right? But right now, that's not the question, really. I mean, I'm asking that to kind of make sure that you guys remember continuity, because when we actually start doing continuity questions, people have a lot of trouble with those. But right now, this was two different questions. What is the limit? The limit is 5. What is the function? The function is 5. They're equal, so it's continuous. What is the limit? The limit is 5. What is the function? Maybe the function's 7. They're not equal, it's not continuous.
Okay. I see.
And in a second, I'm going to summarize this so that we can have written down exactly what we have to do in each case. And hopefully that will make it really clear for you. Okay, so what do I get down here for the limit as x goes to 3 from the left?
7
7. And what do I get when it had 3 from the right?
minus 1.
Minus 1. So now this is a time where we really do have to check. Are these things equal?
No,
No. So what does that tell me about the original limit?
it doesn't exist.
It does not exist. So here, does not exist is my final answer. So that was one question. Yeah, what's up?
Like, we already know by defining it as a breakpoint, we know that the values aren't equal. So like, isn't this kind of
We
pointless?
don't actually know that. And not the next problem, but the problem after that. So we're going to do 2 more piecewise functions. And in the second one, we're going to see that actually sometimes they'll be the same.
Okay, but the definition. Okay, never mind.
So like, think about it. And I mean, I'll draw a picture for us when we get there. But like, let's say that they just so happen to start and stop at the same y value.
Okay.
You see what I mean? Like, potentially they could meet right there and those values could end up being the same.
Okay.
Does that make sense?
Yeah, it makes sense.
Okay. Okay, so then what if I were to now ask you about f of 3 itself? Which interval is 3 on?
The bottom one.
The bottom one. You got it. So that means here, oops, I'm going to plug in 3 minus 4, and I'm going to get -1. And -1 is my final answer for that. And this is because 3 is on the second interval. That straight line right there tells me that. Is this function continuous at 3?
No.
Okay, so we said this originally from looking at the graph. We could see that it wasn't continuous. And what kind of discontinuity does it have?
Jump.
A jump. The left and right are different. We saw that from the graph. Now we're seeing it from the limits. Oops. This is a jump discontinuity. Okay, so let's just take a second to summarize what we did here. So to evaluate piecewise functions, we kind of have 2 different things going on here. The first is if that a value is not a breakpoint. If it's not a breakpoint, we used our intervals to pick the appropriate function and plugged in. If x equals a is a breakpoint, we evaluated the left and right-handed limits separately. And Alex, does that help you with the question that you were having earlier?
Sorry, repeat that.
Does this help you with the question that you had earlier?
Uh,
Or do you still feel a little confused?
uh, can you like explain it real quick? Sorry, I was writing down. I didn't really hear what you said.
Okay. So basically we said we have two different situations here. We have the situation when x minus a is a breakpoint, is not a breakpoint, and then we have the situation where it is. So we said if it's not a breakpoint, oops, we use the intervals to find the appropriate function and we plug in.
Okay.
We said that if it is a breakpoint, we evaluate the left and right-handed limits separately.
Okay, yeah, that answers my question.
All right, you guys ready to do another question? Does anyone need me to move this back down for you to see what I have up there? So we have this piecewise function. What's my breakpoint?
0.
0. So before I even ask you guys questions about this, I want us to figure out what goes with 0 from the left and what goes with 0 from the right. So am I going to go to the top or the bottom for 0 from the left?
Bottom.
Top.
So 0 from the left, I just heard top and bottom. 0 from the left, that's values that are smaller than 0. So that would be like negative numbers. Which interval gives me values smaller than 0?
The top one. Wait.
Oh.
The top one. So x less than 0, that's going to give me values smaller than 0. That's 0 from the left, which means this other one is 0 from the right. Let's answer some questions. We'll start with -4. What interval do I need to go to for -4?
Top one.
Top.
The top one. So I replace g of x with -4. And then I plug in. And I get 28. And that's my final answer.
Where'd you get the 4 from?
Where did I get the -4 from?
Yeah.
That's just the question I'm asking you. Like
Oh.
the question itself is, we can call this A. The question itself is the limit as x approaches -4.
Okay.
Yeah. And so then the next question is g of -4. So what's g of -4 going to be?
28.
28 as well. -4 is clearly firmly in that interval. This is just 28. Is this continuous at x equals -4?
Yeah,
Those
because
two
they're
values are
equal.
the same. What's that, David?
No, I just said yeah because they're equal.
You got it, exactly, yes. They're the same. This is continuous. Yay, we like continuity. C and D. Which interval am I going to go to for 1?
The second
On
one?
1, 2 over
Bottom
x plus 1.
1.
Bottom one?
Yes, to everyone that said that in different ways. The bottom, 2 over x plus 1. So we replace g of x with 2 over x plus 1, and then we plug in to get a 1. And that's my final answer. Are there any questions about this? What's g of 1?
It's 1.
Is 1. So this is equal to 1. Is this continuous at x equals 1?
Yes.
All right, E. Let's look at the breakpoint now. The limit as x approaches 0 of g of x. This is the breakpoint, which means we need to look at the left and right separately. The limit as x approaches 0 from the left of the function, and the limit as x approaches 0 from the right of the function. What am I going to replace g with for 0 from the left?
X squared minus 2x plus 4.
Perfect. And when we plug in, we get a 4. What am I going to replace g of x with for 0 from the right?
2 over x plus 1.
2 over x plus 1. So when I plug in, I get a 2. Are these two values equal?
No.
No. So what's my final answer up here?
It's discontinuous.
It is discontinuous, but what's the answer to the limit?
Doesn't exist.
Does not
Doesn't
exist.
exist.
You got it. So it does not exist. And now I'm just going to look at F before we go talk about continuity. What's g of 0? Which function am I going to go to for when it equals to 0? You got it, Luca. 4. Because less than or equals to 0, which means I go to the top function. Are there any questions about that? Good. So, is this continuous? Not continuous. What kind of discontinuity does this have?
Jump.
A jump, you got it. What's going on with this right here? There we go. So this is a jump discontinuity because the left and right are different. This time we didn't have the graph to rely on to see that, but we were still able to see that from the limits. The left and right were different. Okay, so we're just gonna do one more final question. Any questions about this before we look at the last one? Okay, so then, sorry about that. Let's look at our last example. So our last example is going to be a little bit different. We're going to call this h of x. It's a little bit different because instead of just having 2 functions, this piecewise function is defined by 3 different functions. What are my breakpoints, or what is my breakpoint?
1 and 4.
Points at 1 and 4.
1 and 4. There are 2 values that show up in my intervals here, which means that I have 2 breakpoints. Those breakpoints are 1 and 4. So I'm going to do what we did before, and I want to determine where is 1 from the left and where is 1 from the right. Where is 4 from the left and where is 4 from the right? So which interval do I need to go to for 1 from the left? First, second, or third?
The first one.
First one.
The first one, you got it. So we're going to write 1 from the left here. What about 1 from the right?
And the second one.
The second one, not the third one. Even though those values are bigger than 1, we want values that are bigger than 1 but really close to 1. We're always going right to the right side of 1 and just looking really close and then getting closer. So 1 from the right would be like 1.0001. That's on this interval. Where's 4 from the left?
And the second one.
The second one. And then 4 from the right is the third one.
But if it's on exactly 1, it's neither, right?
If
There's
it's, say
no
that one more
line?
time.
If it's on exactly 1, it's on neither of them because there's no line underneath the.
Exactly, exactly. And so we're going to see that in just a second. G of 1 in this case is not defined. That 1 is not in the domain of this function. So let's start with that actually. Let's look at the first breakpoint. The limit as x approaches 1 of h of x. We know we're going to have to look at the left and right side because this is a breakpoint. So we're looking at the limit as x approaches 1 from the left of h of x, and the limit as x approaches 1 from the right of h of x. So the first thing we did was we figured out which function goes with this, so we can just immediately replace h of x. So as it goes to 1 from the, oh, I don't know why I just changed that left to a right. That's awesome, Audrey. As we approach from the left, we said that's our first function. So we have 4 minus x. And we get a 3. As we approach from the right, that's our second function. And we also get a 3. So this is the question that David was asking earlier. Don't we know that they're always going to be different? We don't actually, because notice that both of these functions, while they are different, have the same y value at x equals 3. So here we have 3 is equal to 3. What does that tell me about the limit itself?
That it's 3?
That it's also 3, exactly. So the left and right were the same in this case, so our limit itself was 3. What about, though, if we look at h of 1? And so this is what Luca was saying a second ago. Is there any line that goes with the 1?
No.
No.
I have x less than 1, and I have 1 less than x less than 4, so I have x greater than 1. I don't have x equals 1 anywhere. So what's the answer?
Doesn't exist?
Does not exist. And this is because we never have x equals 1. Which would be like a straight line under the inequality. Is this continuous?
No.
No. because even though that limit exists, it doesn't equal to the reality. So this is what kind of discontinuity?
Removable.
You got it. The left and right are the same, but it's not equal to the reality. This is a removable discontinuity. Great job. Now let's look at our other breakpoint. So we're going to be looking at the limit as x approaches 4 of h of x. 4 is my breakpoint, so we need to look at both sides. We already checked before we even started where 4 from the left is and where 4 from the right is. So 4 from the left was the second function. So that's 4x minus x squared. And when I plug in 4, I get 0. And 4 from the right was the third function. This is the first time we've seen this. That's just a number. What do you think that limit is?
5.
5. Because it's always 5. What that's saying is it's 5 for every single x value all the time, no matter what. 4 is an x value. Doesn't matter what the x value is, that's 5. So the answer here is 5. Are these things equal?
No.
Nope. So here we get that this does not exist. Now for the last question we're going to ask about this one. Actually, no, I'm going to ask one more after this. H of 4. What's that going to be?
It's going to be 5.
It's going to be 5 because that's where my equals sign is. We can see the less than or equal to, that goes with 4. Is this continuous?
No.
What kind?
It's a jump discontinuity.
It's a jump again because the left and right are different. You got it, David. So this is a jump discontinuity. We're just going to look at one last one. The limit is x approaches 3. Which function should I put here? The first, the second, or the third?
Second.
The second. 3 is clearly between 1 and 4. So we're going to that second interval. So I plug it in, I get 4 times 3 minus 3 squared. That's 12 minus 9 to get that final answer of 3. And what about h of 3? Gonna be the same thing. You got it. It's also gonna be 3. Is this continuous at x equals 3? Yeah. Perfect. Okay, so before we finish, I want us to actually take a look at what the graph of this thing is going to look like. We already saw the graph of a piecewise function with 2 different functions. What is this going to look like? And how it has that removable discontinuity and that jump discontinuity. How is that going to show up? So do you guys all have the function in front of you? Can I do this so that I have room?
Yeah.
Okay. So just that we can kind of visualize this thing right here. We have our 2 breakpoints. The first breakpoint is 1, and the second breakpoint is 4. On the right side of 4, what value does this function take?
5.
5. On the right side of 4, this is always 5. Oops. So I'm going to have my open dot there, and then we're basically saying this is just a straight line. It's always defined by 5. Between 1 and 4, what function do we have?
4x minus x squared.
4x minus x squared. What shape does that take?
It's a quadratic, so
Quadratic, which means
it's like I think it's a bowl, is it? No.
it's a parabola. Is it a happy parabola or a sad parabola? It's a sad parabola because there's a negative in front of the x. It's 4x in front of the x squared. It's 4x minus x squared, which makes this a sad parabola. Now, when I'm graphing this thing, let's do this using our limits like we were doing with our graphs yesterday. 4 from the left is going to 0. Well, 5 from the right we already have in. So 4 from the left was going to 0. So that means I have a little hole there with the tail. All right, and I know this is a sad parabola, so I know it's going to look something like that. To figure out about what it looks like, I'm going to go to 1. And I'm going to look at what's happening at 1. And I'm just going to graph the little things for 1. 1 from the left and 1 from the right gave me a 3. So that means at 1, 3, I'm going to put a little hole here, and I'm going to have tails going out both sides. I know the shape this has to take, and I got to connect these things, so this is going to look something like that. Oops. You guys see what I mean there? We drew the tails with the limits, and then we're saying we got to connect them, but this time I know exactly what shape I have to use to connect them. Now, on the left side of 1, what function do we have?
X minus 4.
4 minus x, yeah, 4 minus x.
Oh, 4 minus x.
What shape is that?
Straight, and
Straight
it's
line.
downwards.
And is it going to be like this, or is it going to be like this? What kind of slope is it going to have? Am I going to go up away from the point, or am I going to go down away from it? You got it. It's 4 minus x. It has a negative slope. So that means my line is going to look like this. Ah, crap. That was lovely. 3, we had that. We have our little tail out, good. So then we have our line doing that. Am I done, or is there one last thing I have to do here? At my breakpoints, right now I just have open dots. Do I need to fill any of those dots in?
There's a closed dot at the. Wait, I don't remember. Is it 5?
So when we look at this, what was h of 4 equal to?
H of 4 was equal to 5.
You got it. So that is exactly where we're going to put the closed dot. That h of 4, we're going to close that dot at 5. So here I was able to use the limits to kind of place things, but also my knowledge of like what functions look like, parabolas and straight lines, to get an actual graph of this thing. And you can see now, we can actually see that jump discontinuity that happens right there, and we can see that removable discontinuity that happens right there. Are there any questions about this? You guys feel like you could regraph this on your own? Awesome. Well, guess what? I'm done. I don't have anything I can do in 5 minutes. So unless you guys want to do another piecewise function, we can be done. No, you don't. All right, then I will stop recording.